Hello friends, in our last lecture we discussed about two different mapping techniques in cache memory. Number one, direct mapping system, and number two, associative mapping system. In this lecture, we'll discuss one more important mapping technique, which is set-associative mapping technique. Now what is set-associative mapping technique and why this is important, we'll discuss in this lecture. Also, we'll discuss some of the numerical examples in this lecture. So I hope this video will be very interesting for you. Let's start about set associative mapping. So now in the last two videos we have seen what is mapping, what is direct mapping, and what is associative mapping. If you see in direct mapping, what is the main funda? The main funda is memory block 0 can be placed in CB0 only. Memory block 1 can be placed in CB1 only. Means there are some reservations. Only on that reservation seat only your memory block can be seated. But in the associative mapping, what we have seen is just the reverse way. You can say almost reverse. Your memory block can occupy any empty space wherever it is possible. Alright. Now set associative is a kind of, you can say, remix technique. You can half of the concepts from from associative mapping and half of the concept is from direct mapping. So here what we are doing, MB0 you want to place it somewhere in CB or click cache block. Then in direct mapping we know MB0 will come to CB0 only. In associative mapping this MB0 can come anywhere. But in set associative mapping this MB0 can come to set 0 any cache block. Means MB0 will come to set 0 only. Inside set 0 it can take any cache block. Now what is set now? This is a new concept here. Set is, in set associative mapping, we again further group the cache blocks into some sets. Now this size should be equal. If you are taking two cache blocks in one set, then we call it as two-way set associative mapping. If you are taking three blocks in one set, then we call it as three-way set associative mapping. So here the example of two-way set associative mapping, where I had total 4 blocks, I divided into two parts, set 0 and set 1. Understood that? Now MB0 we can come to any memory block, cache block, but inside set 0 only. MB0 set 0, MB1 set 1, MB2 set 0, MB3 set 1, MB4 set 0. Set 0, but inside set it can occupy any one of the spaces. Understood that? So for example, I will take the same example, say this 15, again your processor is asking for this 15. We know in direct mapping we have divided into 3 parts, in associative we have divided into 2 parts, in set associative again we will divide it into 3 parts. Rightmost is for a word, you know what is word. So 2 bits are necessary because I have only 4 words. So this one will come here. Next few bits will be reserved for determining the set. So how many sets are there? 2 in this example. So how many bit I need? 1 bit only to determine the set. So this is set bit. Rest all 4 bits will be reserved for tag. So why this tag is necessary now? So in set 1 or set 0, how many possibilities are there? In set 1 I can have memory block 1, memory block 3, memory block 5, memory block 7, memory block 9, like this. So many blocks can be possible, right? So if it is 0000 means memory block number 1, 0001 means memory block 3. I am talking about set 1. If it is set 0, then 0000 means MB0. 0001 means MB2, because MB1 cannot come in set 0. Understood that? So we know the tag is 0001, set number is 1. Set number 1 means I will come to this particular set only. Word number is 11 means I will go to the last word. I don't know, it can be CB2 or CB3, anywhere. You take any one, say I am taking CB2. So CB2, I know I will search for only this one. Now can I say that this block is occupied by this block only? For that this tag will help you. Which block is there? 0001. So what is 0001? 0000 means memory block number 1 can be coming here. 0001 means memory block number 3 can come here. Yes, it's matching. Memory block 3 only I need. 15 is there in memory block 3. So this is how it works, set associative mapping. So we have same example here. The address is generated by processor is 11000. This is the cache size. This is the main memory size. In cache we have two sets, set 0, set 1, and each set I have two blocks, and each block I have two words. So how many bits are necessary to get a word? 2 bits. Sorry, 1 bit, because two words. So this black means word. Next, how many bits you need to get the sets? 1 bit, because you have only 2 sets. So this is for sets, and rest all for tag. I hope you understood. Now we have some interesting examples also. I'll solve those examples. It will be more clear for you about set associative mapping. Just read the question very carefully. What we have? Consider a two-way set associative mapping. So what is two-way set associative mapping? Means in each set we have two different blocks. Fine. The size of cache is 16 KB. So what is the size of cache? 16 KB. With block size of 256 bytes. Remember, whenever word size is not mentioned, 1 byte equals to 1 word. You have to understand that. So means in each word, how many bytes are there? How many words are there? 256. Fine. The size of main memory is 128 KB. Find the size of tag, set, and word. Whenever you get this kind of problems, first you determine the size of main memory. Focus on main memory. As I told you, processor will always generate the address as per the main memory size, not as per the cache size. So what is the size of your main memory? 128 KB. So how many words are there in main memory? 128 into 1024. It's in KB. So 128 into 1024. So to determine the word out of all this 128 into 1024, how many bits you need? How many bits will be there in the address? So it will be, let me explain from here. Yeah, the size of main memory 128 KB, right? So if it is 128 KB, the total number of bytes will be 128 into 1024. Now to get any one of this word, how many bits you need in the address? I need total 17 bits. Why 17 bits? Count it. 128 into 1024. So 128 is 2 to the power 7. 1024 is 2 to the power 10. So total I need 10 plus 7. 17 bits to get any one of this word. So first thing we know that there are 17 bits. Fine. So the address is containing 17 bits. Fine. Next, what we have to find? How many bits will be there for word? Now in each block, how many words are there? 256. It's given, right? 256 bytes. So to get any one of this word from any block, so how many bits I need? Can you tell me? 2 to the power 8 equals to 256. So I need 8 bits to determine the number of words. Forget about set and tag. First of all, I think it's clear for you why it's 17 bits, because of the main memory size. Main memory size is 128 KB. 128 KB means 128 into 1024. So 2 to the power 7 into 2 to the power 10 equals to 2 to the power 17, means 17 bits are necessary to get any one of the words. So out of 17 bits, I need 8 bits to represent the words, because 256 different words are there in each block. So 2 to the power 8 equals to 256. So 8 bits are necessary for word bit. Next, I need set. Now can you tell me how many total sets are there in your cache? What is the cache size? 16 KB. Now what is the block size? 256 bytes. How many blocks are there? First tell me how many blocks are there. So you have 16 KB divided by 256. 16 KB divided by 256 is nothing but 64. Means total 64 different blocks are there. You understood that? There are total 64 blocks. You understood that, right? Because total size is given and the block size is also given. Just divide it, you will get the total number of blocks. So 64 is the total number of blocks, but this is not the set size. How many sets will be there? Two-way set associative means in each set you have two blocks. So if you have 64 blocks, you have total 32 different sets, right? So if there are 32 different sets, to determine any one of them, I need 5 bits, right? 2 to the power 5 equals to 32. So I determined word, which is 8. I determined set, which is 5. Now rest all will be for tag. Fine. How many? So 17 minus 5 minus set, whatever is there, all will be for tag. I hope this is clear for you. So we have one more example. A block set associative cache consists of a total of 64 blocks divided into 4 block sets. Means it's a 4-way set associative mapping. In each set we have 4 blocks. The main memory contains 4096 blocks, each containing of 32 words. How many bits are there in each tag, set and word? Now I told you this kind, if you get this kind of question, then first determine the main memory size. What is the main memory size? 4096 into 32. So 4096 into 32, how many total bits you need to get any one of these words? It will be 2 to the power 5 is equals to 32 and 2 to the power 12 equals to 4096. So it will be 12 plus 5 again 17. So you need 17 bits. So out of 17 now you have to divide it into 3 parts: word, set and tag. Now tell me how many bits will be necessary for sets and how many blocks will be necessary for words. Now what says each block contains 32 different words. It's already mentioned. Whether it's main memory or cache, we know the block size is exactly same. So to get any one of the word out of this 32, how many bits I need? 5. So we have already determined 5 bits for word. We have already determined. Now how many sets are there? There are total 64 blocks, and in each block I have 4. There are 64 blocks and I am dividing it into 4 parts. 4 blocks equals to 1 set. So total how many sets will be there? 16. To determine any one of these I need only 4 bits. 2 to the power 4 equals to 16. So out of all the 17 bits, this 5 bits for word and 4 bits for set. Next all will be for tag. So it's very simple, I guess. So I have one more question. A block set associative cache consists of a total of 64 blocks divided into 4 block sets. The main memory contains 4096 blocks, each consisting of 128 words. Now this is a homework I am giving to my students. Please solve this problem and let me know your answer in the comment section. I will verify and I will let you know if you have done any mistake. Please note down the question. Okay, so that's it for the day. Thank you so much for watching the video.